Hi, this is John. This video is on building a rocket for Level 2 certification. I call it Certify in Style because we're going to do more than just build a basic rocket and fly it on a J motor. In particular, we're going to incorporate electronic dual deployment and fiberglass the airframe. This is more than is needed for a Level 2 certification, but these are techniques that you'll definitely want to incorporate for larger rockets when you get up into the J-K impulse range. So the first decision to make is whether you go kit or scratch build, and if you go kit, which one. For this video, I'm going to build a Lock Precision Easy I-65 kit. Lock kits are great choices. They're inexpensive. They use materials that can be worked with normal tools. In this case, heavyweight cardboard airframes, plastic nose cone, and plywood fins and centering rings. These are familiar materials, can be worked with the tools you already have, and are good high-power rocketry materials. The other thing that you should look for in a kit if you want to use electronics is a separate payload space, which allows for the electronics and dual deployment. And I would recommend for Level 2 rockets, you go with a 54 millimeter motor. There are Level 2 motors for 38 millimeter, but 54 gives you the most choice. If you do want to fly a 38 millimeter motor, you can adapt down, but you can fly a whole range of motors in the Level 2 impulse range in 54 millimeter.
First up is fiberglassing. Now I want to be clear about the purpose of this. Many people think that fiberglassing is necessary for in-flight stresses, and that's simply not true for normal sport flying. These materials have flown on many rockets over many years, including through Mach transitions, with ordinary techniques. What fiberglass really helps you with is providing a hard skin, which avoids dents and dings during transportation and can give you some protection during landing and if the rocket's dragged along by the parachute. So we're going to fiberglass this to give us a nice hard skin, but this isn't strictly necessary to fly this rocket on Level 2 motors. Here's 4-ounce fiberglass cloth. I think this will make a good choice for a skin on these tubes. Heavier cloths, such as 6-ounce, add more strength, but they also add more weight, and the larger weave requires more work when filling. For a nice hard surface on these tubes, I think 4 ounce is a good choice. Now the technique that we use for fiberglass is also important to consider. Fundamentally, what we're doing is we're taking this fiberglass cloth, impregnating it with epoxy, and then wrapping it around the tube. But we want to make sure that it's tightly wrapped around the tube and that it's even so there are no bubbles and no wrinkles. And to do that, it's nice to have an outer wrap. If we wanted to remove the maximum epoxy and provide a rough surface for subsequent bonding, we would choose a porous fabric such as this Teflon release, because the epoxy can migrate through it and be removed. In our case, since we're just going to finish afterwards, we'll use Mylar as a wrap because that will keep the epoxy in the matrix, and the epoxy will help to fill up the weave, reducing the amount of time it takes to finish. The technique of laminating using Mylar is shown in more detail in my fiberglass video. The first step is to prepare the tubes. I like to sand the surface. We don't want to overdo it with paper tubes, so 150 grit paper is a good choice. We just want to take any shininess off so that the epoxy can wick into the fibers and make a strong bond. Before I apply the fiberglass, I like to tape up the inside of the tubes. In this case, the tubes are pre-slotted, so I want to run a piece of tape inside so epoxy doesn't get in, and also like to have tape along the inside edge, and then a little bit of paper so that when I'm working with the tube and my hands are full of epoxy, I don't get fingerprints on the inside. One of the things we have to be careful with paper tube, though, is that the tape can actually cause it to delaminate. So either use low-tack tape or use a little trick to reduce the tack by applying it to your skin first and then applying it. Your skin has oils which will fill some of the stickiness and reduce the tack of the tape. Now we have our tubes all taped up inside, so they'll be protected from epoxy, and we'll have a nice clean skin on the outside with no mess on the inside. One of the things that's changed since I made my fiberglass tube wrapping video is concern for safety and exposure to chemicals such as isocyanates in epoxy. So be sure to protect yourself, take all the appropriate precautions, and check out my shop safety video to make sure that you're keeping yourself healthy. Once the epoxy has reached the leather stage, which is no longer wet but still slightly flexible and a bit sticky, you can trim the excess. You can also wait till full cure, but it's slightly easier to trim the excess at the leather stage. I'm actually not going to take the mylar off until full cure, but trimming off the excess epoxy can be nicely done earlier. Always using a new blade, carefully cut along the edge of the tube, the ends and the slots. You want to be very careful when doing this so you don't cut into the paper tubes. The excess epoxy and glass trims off really easily with a sharp blade at this stage. We can cut through the mylar and through the excess epoxy and make a perfect edge. So once your tubes cure, you can pull off the mylar, and now your parts are ready to build the rocket. I'm not going to go into great detail on building the rocket here because the techniques are pretty much the same as those in my Certified Level 1 video. The main difference is that we're going to use this coupler as the base of an electronics bay. And as far as electronics to put in that bay, we're going to use a great little unit, the MissileWorks RRC3. The EasyEye65 is a pretty standard arrangement with a main airframe and a payload bay joined by a coupler. We're going to use that coupler for our electronics bay and work dual deployment into this rocket. So if we built this stock, we'd put the single bulkhead at the aft end of the coupler, and the single deployment event from motor ejection would separate the forward section with the payload bay and the nose. But instead, we're going to make an electronics bay out of the coupler, giving us the ability to separate forward for the drogue and aft for the main, giving us dual deployment. Of course, we could also do the opposite and separate first at the aft, which is more traditional. However, this rocket has a much smaller forward payload section than aft, so it's easier to pack the main into the larger space. Here's a pretty traditional electronics bay arrangement. We've built the bay into the coupler. The top has a fixed eye bolt. There's a spine that runs through, and the bottom is a cap that's removable. We'll epoxy this halfway into the airframe, and then we'll have the forward section. This will couple into the main tube and the aft section. And even when this is epoxied in, we can remove the plate and have easy access to the electronics. And here we have the electronics mounted into the bay. It's convenient if you can design your bay so they sit nicely to work on and to program and to test. But all that really matters is that the bay is properly sealed from any ejection gases. We have our RRC3, and I have a 2-cell LiPo battery which will provide plenty of current. I also like to wire my bays with a switch because I think it makes them neat and tidy, but a lot of people prefer just to use twist and tape. That is, leave the wires outside the rocket, twist them together, and then tape them to the outside. Whether you use the switch or not, you need a way to easily enable and disable the altimeter, both for testing and in case you need to take it off the pad after it's been armed. And speaking of bays, you can also take advantage of the space in the nose cone.
If you use the stock nose cone, I suggest adding a little strap so that there isn't metal pulling on that plastic loop. But you may also want to watch my nose cone mods video and get some ideas on building a bay. This is a great place to put a GPS tracker or some other electronics that you're interested in flying.
Now we need to select the ejection charges for our rocket. We have 2 events, so we'll need 2 charges. Here I'm using an online calculator from Info Central to calculate the amount of black powder. Start with the pressure towards the low end of the range. Here I've selected 10 psi.
I go over making charges in much more detail in my electronic recovery video. Here we're going to make up a charge just as we would use it in the rocket, according to the estimate that we got from the black powder calculator, and test whether or not it's sufficient. Okay, let's test out this ejection charge. We load the charge in to the section of the airframe. We don't need to install electronics, we can just have the wire coming out of the hole. But we obviously want to make sure our nose cone is the way it's going to be, installed into the airframe. If you're using shear pins, install the shear pins. Here I'm using 1/16 inch styrene as a shear pin. Get it started. Push it through, tilts through the nose cone. So the other thing you want to do is catch the nose cone so if it flies off, it doesn't do damage. And then all we do is fire the charge. So I would say that is a satisfactory ejection. And finally, when testing the ejection charge on the aft section, make sure to install a motor, probably the smallest motor that you're going to fly, and secure it. You don't want to leave this empty because then the ejection charge is released through the motor mount tube, which isn't realistic in flight.
Let's look at what happens inside the rocket. With the motor installed, the inside is a more or less sealed space. Not perfectly sealed, but reasonably well. When the charge goes off, gas expands, filling that space. Eventually the space is full and the pressure is more or less equal, putting force in all directions. The only part that's free to open is the separation, which opens, releasing the pressure into the outer air.
Once the rocket is finished, you can get a preliminary weight to figure out the size parachutes you need. For the main deployment, make sure to include not only the weight of the rocket, but also the burnout weight of the largest motor you plan to fly. For dual deployment rockets, especially if you're flying in hard surfaces like a desert playa, I usually go up a size, round up to the next size, just because since it's dual deployment, it won't be falling that far on the larger parachute and it gives me a little softer landing. For the drogue, you generally want it to come down about 3 times as fast as the main. If your main is coming anywhere in 15 to 20 feet per second, you drogue anywhere in 50 to 60 feet per second or even higher. The main thing about the drogue is just a controlled descent until you get low, and then you get the slow descent on the main parachute. And of course, an important aspect of style is the finish. I like to get a nice finish on my rockets. I think it makes them look better and fly better. But however you finish your rocket, or even if you don't finish it, make sure you've got it ready to fly before you get the weight and final center of gravity. Get the CG, or center of gravity, by balancing the rocket and measuring the point from the tip. This is better than using the simulator to estimate it because you'll have an exact value that you can enter. So there you have some tips on a level 2 certification rocket. I hope you enjoyed the video, and I hope you have a perfect flight and an easy certification.